Do you do the very quickly? All right, section 12.4 was about what, guys? Alright, so, SmartBoard's not working. Alright, section 12.3. We will go ahead and, if we have time at the end of class, grade that homework. Otherwise, we're going to jump into 12.4 because time is short. You guys took these notes and have them all ready to go yesterday. So, let's jump in. Ready? Looking at the graph that you guys have. Christian. Where's the horizontal axis? At 1/2. Because I'm looking for what horizontal value the graph is getting, the y's are getting closer and closer and closer to. Question, what's that savvy word that we've been learning in this chapter? Getting closer and closer and closer to that? Approaching. So, maybe a long time ago when we talked about horizontal asymptotes, we used vertical asymptotes. And when we would say something like getting closer and closer, we would say something like getting arbitrarily close to. We would say something like getting closer and closer but not touching. Maybe we were meaning approaching the whole thing. And maybe that's why approaching wasn't a brand new word this chapter, because you guys already saw approaching when we went a little arrow, remember? A little arrow back in horizontal asymptotes, and you're going to see today how you guys actually learn limits in some of the first few chapters of the year. Horizontal asymptotes. Way back when we talked about end behavior. End behavior, as you go to the ends, and as you go to the ends and beyond, you can go to the end either going to positivity, which we could say is headed to what direction? I'm going to positive, to the right, and if that's approaching negative infinity, to the left. Good, so I can say to the right and to the left. Now question, how is this different than the approaching that we've been doing all chapter 12 long? I want you guys to write this down, but what if I was to say something like the limit as x approaches 1 of x plus 1 over x minus 1? How would we solve that limit? Go write it down. It's in a different section, a different example. So how would we write it down? Or how would we start solving it?
Could we use direct substitution?
Okay, direct substitution. So if we plugged in, we would get 1 plus 1, which is 2, over 1 minus 1, which is 0. How would we keep going? It's not 0 over 0. It would be 0 if it was flipped. It does not exist, but does that mean D-N-E? Get out your calculator. Look at your graph. We haven't talked about this one. This is sadly one of those sections that we're going to have to skip. Okay. We're going to graph this function. Remember, it's our fallback. What do you guys see going on at 1? X plus 1 over x minus 1. It has the horizontal asymptote, but I meant at x equals 1. Not y equals 1. What's a line called vertically? That's not touching it? Vertical asymptote. Okay. As we come in towards 1, wait a minute. How do we approach 1? No, we do. We need to. How do we approach 1? Limits. How does x approach a constant? No. How do we approach 1? How many different ways? From both sides. What happens at 12, 1, 12, 2, and 12, 3? Okay. As x approaches 1, how do we approach 1 on the graph? From below and from above. From the right and from the left. We're coming in towards 1. From below for you guys and from above. From the left and from the right. Right? So remember how there has to be one-sided limits and they need to, what do they need to do in order for the limit to exist? They need to agree. So what do you guys see as the function comes in towards the vertical asymptote from the left, from below? Where is the function approaching? Do you remember that way of putting the sign to say from below? Yeah, the negative. And then Sean says coming towards negative infinity. Do you guys agree? Good. So I would answer negative infinity. How would I answer the limit as I'm kind of reviewing like 12.1, 12.2, and 12.3 all at once? How would I answer the question 1 from above? Positive infinity. So how would I answer the overall limit? Yeah. Why DNE? They do not agree. If the one-sided limits do not agree, the limit does not exist, right? Okay. So with that, how is this process different than if I was going to infinity instead? Yeah, exactly. It all comes down to one word. You're going to the right and to the left instead of what we were doing a second ago. From the left and from the right. For a limit that is approaching a constant, for this kind of limit where x is approaching a single number, I come from the left and from the right and I compare. Now why am I about to erase all of that? Because we're not in section 12.1, 12.2, 12.3 anymore. What's going on with horizontal asymptotes? I'm not coming from, I'm going to. To the right without bound, to the left without bound. I'm thinking about the end behaviors. We're going to think degree tests, and we're going to think numerators versus denominators. You guys remember that from the old school days? So horizontal asymptotes. What do you notice about this one up here, though? Without me even really teaching anything, I mean, you guys wrote down some notes yesterday. But if I was to say the limit as x approaches infinity of the function, and the limit as x approaches negative infinity of the function, question, how would you answer these limits? What would you say? How about for the first one? X approaching infinity, where are you going? To the right. And as you go to the right, what are the heights doing? What are the y's doing? Not getting smaller forever, though. They're getting lower, but closer to. Okay, so what's the limit as x goes to infinity of the y values? And what's going on as I go to the left, or as x goes to negative infinity, my y values are getting higher, but it's bounded and getting closer and closer to what? The 1/2. So what's weird is that we say, hey, a horizontal asymptote, it'll never touch, but question, does the limit exist? And the answer is yes. It's getting closer and closer and closer to the left. Oh, sorry, that's to the right, huh? To the right towards 1/2, and to the left, where is it getting closer and closer and closer to? 1/2. But these are two separate limit problems. These are two separate limit problems. And I will wait. Am I going to wait? Yeah, I'll wait to show you a crazy example of where they are not the same number. It's possible they're not the same, which is why we have to remember these are two separate limit questions. All right. You guys wrote down yesterday this page, and this page kind of said, if the limit's not coming, if the x is not coming towards a constant from two sides, technically the old informal definition doesn't apply. New type of limit, new type of problem, whole new category. So, in this whole new category, and in this whole new, what do I want to say? Informal definition, we have to talk about limits at infinity. Is there anything weird about saying at? Can you arrive at infinity? So what is the weirdness? Well, it. But what does the limit say? You kind of act as though you're at it, which is a whole other topic for a whole other, not this class day. Limits at infinity exist if, okay, so this is when limits exist, when you have infinities involved, when you're going to the right, to the left, x approaching infinity, x approaching negative infinity. If f of x gets arbitrarily close to L as x increases or decreases without bound. Long story short, there is no coming from both sides of infinity. Why not? How can you get on the other side of infinity to come the other direction? You can't. So, limits at infinity or limits to infinity, if you guys want to think of it that way, you only go one direction, so you're only going one direction. There is no added, hey, the limits have to agree. Because you're just going to the right or to the left. You're not thinking about them both together, and they don't even have to be the same number, and they're not even always. As x increases without bound, that is a limit, as you guys have already seen. As x approaches positive infinity of the function. And as x decreases without bound, that is a limit. That is a limit as x approaches negative infinity. Remember, once again, the first one is to the right, and the second one is to the left. And at the very bottom of the page, even though you guys learned horizontal asymptotes well, back in algebra 2, I think, technically, to actually define a horizontal asymptote, you have to say there is a horizontal asymptote at y equals L if and only if the limit as x approaches infinity of f of x, or the limit as x approaches negative infinity. It doesn't say and, it says or is L. A horizontal asymptote is defined by a limit. When we found horizontal asymptotes in, did anybody look at the table of contents and figure out where it was? We'll go find it. Horizontal asymptotes is when we were talking about and describing functions. We had vertical asymptotes, we had oblique asymptotes, we had poles, talking about rational functions. No rational functions?
Yeah.
Go to 2.6. Turn there. Let's see if we can find it. Because even though you guys had blanks yesterday, you did not have blanks in those notes. Okay, in 2.6, does anybody see anything about horizontal asymptote phase? What?
It says L.
It says L! We just didn't say it was a limit. What? Or maybe I did. You guys didn't. I was teaching calculus from the beginning. Anyways.
Steve Harrison.
You guys act as though I have power over a million things that I don't. Okay. Okay, moving on. Okay, that was being a little aligned. Anyway, okay, so before we get into the degree test, which, wait a minute, didn't you guys write down degree test yesterday? Weren't they there somewhere? Oh my goodness. Wait, what? Where did it go? Where did that go? She's up the air.
Oh.
Once again, well, it's okay because I meant I have no power over technology. You guys see what I love? Make me say I got clothes. Anyway, is it back? Go team. Wait a minute. Don't these look like those? Doesn't that look like that and that look like this? Those of you that actually turned in your notes to section 2.6. Anyway, never mind. Here are the degree tests. We'll get back to them in just 1 second. But first, let's talk about it in a calculus-y way. Ready? This is right where we left off. So the degree tests are coming. That was all that to say. The degree tests are coming, but let's talk about it from a calculus-y approach first, and then say, hey, there are shortcuts that we've learned for forever, and this is why they work. Cool? So why they work. If anyone were to ever ask you as you were doing tutoring hours,
Oh, shoot.
how do
This is think of this.
next Friday? Technically, the next Tuesday, because Wednesday I'm in a
We're
senior
trying to go to Starbucks
session.
before the
I have to
finals.
do- No, next Tuesday.
Wait, so the finals are Tuesday, Thursday, and Friday, and Monday.
Yeah, Monday and Tuesday.
Oh, you're giving us to the.
Finals are Thursday, Friday, and Tuesday. So I'm giving you till the end of the day.
Last year. Yeah,
It is. Alright guys, keep going. Okay, the calculus, the approach to why the degree tests work. And why the degree tests are what they are. Ready? The long story short of it is, if you were to grab your graphing calculators, and I want you to graph 1 over x, and I want you to graph 1 over x squared, and I want you to graph 1 over x cubed. Okay. 1 over x, 1 over x squared, and 1 over x cubed. What's true about all of the horizontal asymptotes? But why? They all have horizontal asymptotes where? Why? But why? Go to your table. Delete out. It should be still an ask, right? Okay. I want you guys to go ahead and plug in, I don't know, what's something that would go to positive infinity? Plug in 10. How do you go to positive infinity? Like a big jump from there. 100? Plug in 1,000? What's going on? Don't think about the table, although it should agree. Think about the function. 1 over 10, 1 over 100, 1 over 1,000.
Oh, because it keeps getting smaller,
Point
smaller, smaller.
0.001. Yeah. Think about the function 1 over x. Is 1 going to change? No. What changes? X. And as I go to positive infinity, 4x to any power, who's going to win the top or the bottom? The bottom. And as the bottom wins, what does that mean? The number is getting smaller and smaller. You're dividing 1 into bigger and bigger numbers, which mean into more and more numbers, which means into smaller and smaller pieces. If you have a pizza, a Costco pizza, well, the big one, okay? And let's say you only want 4 slices that they cut in like their whatever. How big are those slices? Ooh, they're huge. Okay, but what if no, I have a party of 8. What just happened to all your slices? They're cut in half. What if you're like, oh, I have a party of 16 and they don't need much pizza, they're little, right? They're even smaller. What happens when you take 1 unit, 1, and divide it? What happens if you have a party of 100 with 1 cup of pizza?
Oh my god.
Obviously, like this much.
So, yeah, exactly. So, what's going on when you have 1 or any constant over x to any power? As x increases, the size of the value decreases. So what is the function doing? Approaching 0. What happens if you're going to negative infinity? What if you plug in bigger and bigger negative numbers? 1 over negative 10, 1 over negative 100, 1 over negative 1,000. Doesn't matter, even though they're negative, we're still approaching 0 because we're dividing. Whatever number over x you graph, it's going to have the same behavior of a horizontal asymptote at 0. We start there and we define that to be true. If we define that to be true, you guys wrote down yesterday, whenever you have a rational function, which means ratio, which means fraction, you can multiply the top and bottom creatively using 1 over x to the n, where n is the highest degree of x in the denominator, meaning, ready? Example. If I was to take the limit of this expression, long story short, technically according to limit properties, we take the limit of the constant minus the limit of 3 over x squared. What's the limit of 4? As you plug in bigger and bigger x's. Still 4. 4 is 4 is 4 is 4 is 4. Is that changing if you're plugging in x's? No. The limit of any constant is itself. There's no x's to plug in. It's not getting changed by x doing anything. Who cares? 4 is 4 is 4. Minus. But what happens when you're taking the limit as x goes to infinity of any constant over x to any power? What's the idea? What's the have three pieces now. But first you're cutting them into 4s and then into 25s. Well, 4s and then into 9s, then into 16s, then into 25s, and then into 36s, and then into 49s, and then into, anyway, what's still happening to all of our pieces? Smaller and smaller and smaller, so we're approaching as we get bigger and bigger and bigger squares that we're dividing them into. 0. But how do I show that mathematically? I say, well, didn't we just talk about a second ago that 1 over x to any power is 0? So the math of it says, and this is what probably most calculus teachers would teach, that you could go ahead and before saying that 0, you can multiply top and bottom by this known function that we already can say, 1 over x to any power is 0. On top, we're going to end up with the limit as x approaches infinity of 3 over x squared all over, what's x squared over x squared?
1.
1. If you guys want to think about it, although this one is actually one of the easiest probably. We can go ahead and look at this and say, wait a minute, according to the defined statement up above, 1 over x to any power approaches what? 0. And what's 3 times 0? 0. So we can show it. We just have to go ahead and start with the given fact that 1 over x to any power is 0. But if you guys notice, isn't 3 over x to any power going to be 0 too? Or also? And so if we start to get to this general idea of as long as the bottom is stronger, we're dividing faster than we're multiplying. Or you can think we're dividing faster than we're adding. So the pieces are still going to be getting smaller and smaller and smaller. But mathematically, we could say, as long as we can state, which we can, these two facts are true, we can use that in order to show or to solve any horizontal asymptote problem, and thus any limit to infinity or negative infinity problem. You ready for it to get the harder though? Not harder, just more interesting. What would you do on number 1? Or your next example that you guys have written down? Degree test. No, technically not yet. I'm going to show you a couple more mathy ones. What would I multiply by 1 over? What's the highest power of x demonstrated in the numerator or denominator?
X to the 3rd.
So I'm going to multiply top and bottom by 1 over x cubed. Now what's going to happen as I keep going is that I get 5 over x cubed minus, what's x squared over x cubed?
1 over x.
On the bottom I get 1 over x cubed plus 5x over x cubed is 5 over x squared minus 3. Question. How many of these little pieces that we've ended up getting just by multiplying and distributing, how many of these little pieces are going to go to 0? No, they just said find horizontal asymptotes. We can think we're going to infinity because it's a limit. What's going to 0? Is he going to 0? Yes or no?
Yeah.
Bottom wins. Constant over x to a power. Is he going to 0?
Yeah.
Yep. Is he going to 0? Yep. Is he going to 0?
Yeah.
Mathematically, we've shown all of these guys don't hold any weight compared to him. Is he going to 0? No. So when we do the degree test and we say, ignore him, and him, and say, he's the strongest.
Let me see.
We're doing the exact same thing as all of this math to say, wait, pause. And as we take the limit, as we take the limit to infinity, how we find a horizontal asymptote, we can say you're just 0, you're just 0, you're just 0, you're just going to 0. And my final horizontal asymptote is at y equals, what's 0 over negative 3?
Oh, 0.
Degree test, bottom wins. Answer is 0.
But out of the 4, the 2 denominators, aren't they actually x cubed over 1 and x squared over 5? If you actually, because you have like 1 over 5 over x squared, doesn't that flip? And then the top would win?
Oh, in the context of the whole problem, you'd have to get a common denominator with all of them and then flip them.
But technically there would be a
But
flip.
you can't split up a cross addition or subtraction like that. Like when you have addition or subtraction in the numerator, then we can go ahead, part method, and we can separate common denominators, but in the denominator we can't split up. So you're doing a little bit of illegal math.
Okay.
Yeah, doing a little bit of illegal math. I think another way of showing it too. Because Luke is saying you're dividing by the bottom divided by x cubed, so you end up flipping it. But as you end up flipping it, let me talk about that tomorrow. I can show you examples. It's just going to take time. I'm trying to get through more examples. Number 2 is where things start to get a little weird, sadly. Because in number 1, if I was to go to negative or positive infinity, the result is exactly the same. I have zeros and I have like a negative 3 left over, but 0 over, and so the answer is 0. Number 1, it made no difference whether to go to negative or positive infinity. Number 2, if I go to positive infinity or if I go to negative infinity, I might get different results. And here's your introduction to harder functions. Now you guys, if you want to, take a second and I want you to make a guess based on the degree test as to what you think the limit is. And you haven't exactly written them down yet, you see them paying attention, right? But if you look at the degree of the top and the degree of the bottom, what would you guys say? Who wins, top or bottom, or is there a tie? Square root of a squared is like a linear. We can't do it, we can't show it, we can't write it all nice and pretty, but we can say, if we have a quadratic, under square root, the degree is linear. Okay. So since there's a tie, what do we normally do in a degree test? I hear different descriptions. I think the easy shortcut way, though, is the ratio of the leading coefficient. The ratio of the leading coefficients, which would be what? Maybe 5 over 4? Maybe 5 over 2? Interesting. But here's the dilemma. What happens when we do it the mathy way? What's the highest degree? What's the highest degree of x? X to the 1? But shouldn't we technically maybe write it as x squared? For the bottom, just to keep it in context. Does that make sense? Ooh, keep it in context like lesson Bible teachers. Anyway, so context matters. Context matters. Why did I do the top? Because I want them to be equivalent, but I want them to be appropriate for where I need to take them. Does that make sense? Okay. So then, if I was to go ahead and plug and chug, what's 5x over x? Just 5, right? In the bottom, I can bring in that little division. I'm going to end up with the square root of, what's 4x squared over x squared? 4 plus, and what's 1 over x squared? Oh, I guess just 1 over x squared, right? Here's a quick dilemma. Does anybody know a dilemma with the square root of x squared? Is there anything to do with signs that we have to be careful of? Wouldn't a positive square rooted work? And wouldn't a negative square rooted work?
But if the bottom wins, it goes to 0 anyways.
But does the bottom win? I think according to what I see,
NBM.
this little piece goes to 0, and that little piece goes to 0, but who's still chilling down there? The 4. And because of that little square root of x squared, Delio, we have a bit of a dilemma. What's the bit of our dilemma? Because our y's are either positive or negative, we kind of have to add that in, and here's the sad part. Question. If x is approaching positive infinity, then question, what sign should my x's have? A positive. In which case, I would need to make this a positive. And in this one, if x's are negative, I need to choose the negative. Here's the sad or the weird thing, I should say. Is it possible to have two different vertical asymptotes? Pause. Wrap it. Let's
Ooh.
pause.
What about those that go like this? And there's,
Middle that's missing.
and then it continues.
Yeah, it can be all sorts of weird, right? Wrap it. Let's see if there actually looks like there's two or horizontal asymptotes or not. Because that's weird. Like I thought they agreed. Like wherever this one goes, and it's the same thing. Graph this function. Does it look like there's two different? One horizontal asymptote above the x-axis and one vertical asymptote. Sorry, horizontal asymptote below. Struggle. Now, why is that a struggle? Guys, do we want to do the long mathy way all the time? No. And even this long mathy way was kind of abstract. So how could a degree test help us with this? There were two answers. Degree test, we would have gotten 5/4. Oh, wait, that's right. 4 was square rooted. 5/2. But how do we know there's two? The square root tells us beware. The square root tells us beware. Oh, that's an easy pay attention. The square root tells us beware, first of all. And second of all, we had to check the sign. Can you guys look at the very, very beginning? How do we usually find a limit? Plug in, right? So what would happen if, I know this is weird, I'm going to put little quotes around infinity. What if I was to plug in a positive infinity there? And a positive infinity here? What sign would the top have? 5 times a positive number, or positive numbers that are ever increasing. What sign is that? Positive. And if I put in a positive and I square the positive times 4 plus 1, square root it, what sign will the bottom have? Positive. What sign did this answer end up being? Positive. So question, what would I plug in if I was trying to do the other limit? What's going to happen if I plug in negative infinity? Negative infinity times 5 will ever decreasing or ever more negative numbers times 5. What sign is that one always going to have? Negative. But what happens if I put a negative squared times 4 plus 1 square root? What's a negative over a positive? Negative. So maybe there is a way to still use our shortcut degree test and not have to stress. And we'll do the math. We're just going to be really, really careful. We must. Okay, let's just go degree test. Question. We just talked about what happens when degrees are tied. Why am I saying or bringing it up with number 16? What's true about the degrees at the top and the bottom? They're tied. And when they're tied, what is my final limit answer?
2 answers.
3/4 ratio of leading coefficients, right? But wait, I want you guys to write sign. Whenever you take the ratio of leading coefficients, I want you to write sign. Why? Is it positive? Is it negative? Or is it positive and negative? Why?
That's when you plug in the, like, let's say if we did use the negative infinity quotes, the square would make it positive.
I plug in a negative infinity squared times 3 plus 1. Ever bigger negative numbers squared are still going to be positives, right? How about the bottom? Ever bigger negative numbers squared, positives, times 4. Super big, minus 5. The 5 can't take away. What's a positive over a positive? Positive. So whether you plug in a positive or a negative, 3/4 is, we did the sign. We're good. Check. Positive 3/4. Yeah, degree tests. We like them. We just have to be careful of the really weird ones. So degree test. Let's talk about those shortcuts.
So it's
Oh no, I
literally
gave you another weird one. Can you guys do it?
It's literally the same rules as the horizontal.
Horizontal asymptotes are limits to infinity. Just no one ever told you. So no. Ready, set? Do a weird one. See if you can get it right.
Everything connects.
It's all connected.
What? Has a square root. Not bad. Not bad. Think about going to positive infinity. Think about going to negative infinity. We can even do the fuzzy math, but let's not stress about it right this second. You guys think about the degrees. Who wins? They're equal, but why? He has a 4th degree, but he's under a. What would happen if I multiply top and bottom by 1 over the square root of x to the 4th? Does this 10 have any cloud? No. He's just going to go to 0. What do I do with these guys? Square root of x to the 4th is an x squared, so you can say the ratio of leading coefficients. However, when I go to writing down, what would the ratio of leading coefficients be? 4/3?
I know. 4 square root.
Yeah, 4 over square root of 3, because we would have the square root of 3x.
4 square root of 3 over 3.
Yeah, we could simplify. I want you guys to write, oh, there's a square root, let's check the sign. Same thing. Now, why did I write 2 of these separately? My distracted ones up front. Yeah, I have to plug in for a positive or for a negative, because they could be ever bigger positive numbers or ever bigger negative numbers. So, what happens when I plug in wait, hold on. If he's squared and he's to the 4th, everything's going to stay positive, right? Because the negative squared and negative to the 4th, they all stay positive. So he's a positive, he's a positive. Well then, question kiddos, what's my horizontal asymptote? Do I have 1 or 2 or none? 1. I have only 1, and it's positive. And we're doing calculus now, so let's not waste time on rationalizing. So, with that, what's our shortcut for the degree test? If the top wins. You're making pizza faster than you're cutting it up in little pieces. The little pieces matter. We have more pizza. We can say no horizontal asymptote. But if there's no horizontal asymptote, there's still a limit. The limit as x goes to infinity, or the limit as x goes to negative infinity equals plus or minus infinity. It's not a number, but my function's still going somewhere. We just have to figure out which way. And to figure out which way, we are going to check the sign of plugging in. Positive or negative infinity, we have to check the sign. Positive or negative infinity, we have to check the sign. We have to see which way. If the degree of the top equals degree of the bottom, if there's a tie, what do we say? Ratio of leading coefficients, is that right?
Yeah, leading coefficients.
Hold on. What am I going to say as soon as I finish writing the ratio of the leading coefficients? Why? We don't know. We don't know if it's positive or negative. We have to check it, right? On the right side. Does anybody know the answer to the last one so we can get out here quick?
Horizontal asymptote.
0! And we're done. Bye, guys. If the bottom wins, 0, 0, 0,
You're writing
0.
D, like very big, like in the patio.
No need to decide. Positive negative 0 is still 0. Alright, kiddos, work on 12-4. We'll check 12-4, 12-3 tomorrow.
Let's see.
Yeah.
Can we have carnival in this class?
Alright. What do you have done for tomorrow?
I can't get lazy enough.
I know.